Hello everyone. In this video, we will talk about geometric product, and finally, we can talk about geometric product, and it will be the last. It will be the last product to introduce in this video series. So please be patient. We have talked about the dot product between two vectors is not reversible. We have also shown that the wedge product between two vectors is not reversible. If you forget, I give you some recap. For example, if we have a vector A like here, or vector B and point like here, at the end of this vector, we can draw, we first stitch these two vectors together, and at the end of vector B, we can draw the plane, such a parallel to, not parallel, but perpendicular to A. Then the dot product between A and B, we can calculate the dot product between A and B. But if I change the B to here, such that touch this plane, also I change the B, this will be another vector B, and all of them will give us the same vector A dot vector B. It's because the projection from B to A on this when B touch on this plane is the same. So we will call this plane A dot B plane. And it's the same story when in a wedge product. Let's say we have the same setup. Vector A pointing this direction, vector B pointing in this direction, and I can draw a line that parallel with vector A. So, and then I move vector B here, 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 all the vector here when they wedge, when A wedge this vector that touch on this line, it give me the same A wedge B. So that's why A wedge B is also not reversible. But perhaps you can see that from the image, if we want to build some product that is reversible between two vectors, it seems that we can combine the wedge product and dot product together, right? If you look at this image, you see that there's exactly the point. There's exactly, maybe I should change, there's exactly a point here that touch it. That is well defined because a line cross a plane, there will be a point. So yes, this motivate us to define a geometric product like A, geometric product B, that which we will just say vector A, vector B. It's defined. We define it as this is the geometric product, which there's nothing in between. We define them as A dot B plus A wedge B. So that is the we use this definition to define a geometric product between two vectors. And we will also see the geometric product between a vector and bivector and so on. But this image and this setup motivate us to use this definition. Keep it in mind that this definition only define between a vector and a vector. What happens if we want a geometric product of a bivector to a vector? And this is not defined here. This definition only works between vectors. However, in the next video, I will introduce a generic definition, which also not just work on a vector. Of course, with only between vector will give us exactly the same expression, but also define bivector to vector and so on. But in this video, we will stick with this definition since we are motivated by this graph, and this definition will help us to define the inverse of a product, inverse of a vector. Sorry, inverse of a vector. Let us see what is the geometric product between two vectors. What will comes out. Just as usual, we use orthogonal bases, which the basic vector are orthogonal to each other, and it has length 1. So let's look at the case in 2D. We have a vector A is equal to A1 E1 plus A2 E2. That's fine. Same with vector B. Vector B is equal to B1 E1 plus B2 E2. As we have seen before, the definition of geometric product between two vectors is first we use the dot product, calculate the dot product between these two vectors, and plus the wedge product between these two vectors. So now we write the A into A1 E1 plus A2 E2, and B, vector B, B1 E1, B2 E2, and the dot product between them. We know that as we know before, the dot product E1 E2 is 0, E1 E1 is 1. Then we get this part. We get E1. We get the A1 B1 plus A2 and B2. And here we have now we think about the wedge product part. We have learned it before. So we know that wedge product E1 E1 will 0. E1 E2 will create a bivector of E1 wedge E2. So, and this is basically the same with E2 wedge E1, just in the opposite way. So we can reverse the word and put minus sign. What we get is E1 B2 minus A2 B1 with the basis E1 wedge E2. One thing to know is that here this is no longer vector. Maybe we can write it in this way. So this would become A1 B1 plus A2 B2 plus A1 B2 minus A2 B1 E1 wedge E2. One thing to notice, this is a scalar. And this is a bivector. And there's no vector. One thing to notice that there are the geometric product between vector, and there is no vector. Yeah, we have a scalar, we have bivector, and there's a no vector. There is no vector, yes. And it will be the same story in n dimension. So you still have still using orthogonal basis A and B. Then you will end up scalar. And since you have more than one bivector basis, you will have a combination of bivector bivectors, but you will not have vector. You will not have vector back. Yeah, and it's quite important, this the scalar plus the combination of bivector, because we will use this kind of object, which is a scalar plus the combination of bivector to perform the rotation. So this kind of service is related to rotation, but we will talk about this later. And yep, now we can try to find the inverse of a vector in a geometric product. So in this time we don't specify one specific dimension. Instead, we just think about in any dimension, such that vector A is the sum of vector AI. No, it's not vector, but a scalar AI with vector EI. And the I will be the index from 1 to n. It will up to a dimension. And then what we want is to find that, is to construct the inverse vector of A, such that vector A, geometric product with inverse vector A, equal to 1, and the inverse vector A, geometric product with vector A, is also equal to 1. So let's try to now we think about, okay, how this inverse vector A should be. So we can define it in this way, try to define it in this way and see, does it work? So let's define the inverse of vector A is equal to vector A divided by the dot product of the product between vector A and vector A. So let's try. We can do this, and vector A, geometric product with inverse vector A equal to A divided by vector A dot vector A. We know that the geometric product is the dot product plus the wedge product. So we will get vector A dot vector A plus vector A wedge vector A dot vector A. So we know that since the wedge product is anti-symmetry, and which means that wedge product with itself is always equal to 0. So, and you should not be, if you have watched those previous videos, then you should not be surprised. If you have question, you can go back to the video about the wedge product. Then what we have is vector A dot vector A divided by vector A dot vector A is always equal to 1. And it will be exactly the same for the inverse of vector A. Geometric product vector A is basically the same calculation here, and equal to 1. You will also find that A is equal to 1. So now we are able to construct the inverse of any vector that we have. And we will use this inverse property to derive projection and rejection we will show in later in latest video. We will show that a vector x can be written like vector x with geometric product vector a, and also geometric product vector a inverse vector a, and is equal to x dot a vector x dot vector a inverse 1 plus x x vector x wedge vector a inverse vector a, and we will show that this is a projection, and that is a rejection. But if you don't understand right now, it's fine. We haven't talked about this yet, but it just gives us the motivation why we introduce the inverse of a vector here.